Hello and welcome to our channel. Today, we're diving into an exciting project in space exploration and asteroid mapping. If you're curious about the latest developments in space science, you're in the right place. Let's get started. It seems like every month there's a new story about the discovery of thousands of new asteroids. Tracking these small celestial bodies from ground and space-based telescopes helps us follow their overall trajectories. But understanding what they're made of is much more challenging with these remote sensing techniques. The field of asteroid study is not just fascinating, but also crucial for our understanding of the early solar system and for potential planetary defense. Asteroids, those rocky remnants from the early solar system, hold clues to the origins of our planets. By studying them, scientists hope to uncover secrets about the formation of our solar system over 4.5 billion years ago. These celestial bodies can vary greatly in size, composition, and location. Some are as small as pebbles, while others can be hundreds of kilometers in diameter. Understanding their composition is not just a scientific curiosity. It's also essential for assessing any potential threat they might pose to Earth. To really get to know an asteroid, many projects take a more direct approach. One such project comes from Dr. Sigrid Elshot and her colleagues at Stanford, supported by NASA's Institute for Advanced Concepts back in 2018. Their project uses an advanced set of plasma sensors to detect an asteroid's surface composition through a unique phenomenon, meteoroid impacts. But what makes this project stand out among others? Let's dive deeper into its innovative methodology. This project is called the Meteoroid Impact Detection for Exploration of Asteroids, MIDEA. It involves a swarm of small satellites, or smallsats, coordinated around a mothership. These smallsats are equipped with plasma sensors specifically designed to detect the characteristics of the debris plume created when a meteoroid strikes the asteroid. The concept of using swarms of smallsats is not new, but the application for asteroid exploration is a novel and promising idea. Swarm intelligence refers to the collective behavior of decentralized, self-organized systems typically made up of many simple agents. In nature, we see this in flocks of birds, schools of fish, and colonies of ants. Applying this concept to space exploration, smallsats can work together to achieve complex tasks that a single large satellite might find challenging or impossible. The idea is that by having many small, inexpensive satellites, the system can be more resilient and flexible. These impacts happen more often than you might think. According to the researchers, they could map the surface composition of an asteroid down to a 1-meter resolution in about 50 days, even considering some limitations due to orbital constraints. This high resolution is crucial for understanding the small-scale variations in the asteroid's surface, which can tell us a lot about its history and structure. So, how does this system work? First, there's a main spacecraft, envisioned as a CubeSat weighing around 50 kilograms, using a standard propulsion system like an ion drive to travel to the asteroid. The CubeSat design is chosen for its cost-effectiveness and versatility. CubeSats are a type of miniaturized satellite for space research that are made up of multiples of 10 dice 1 cn10 cm cubic units. They are commonly used in low Earth orbit for various applications including communications, Earth observation, and now, asteroid exploration. Once the main spacecraft reaches the asteroid, it hovers a few hundred meters above the surface and deploys a series of small sensor satellites. This proximity allows the sensors to gather detailed data without the interference that would come from observing from a greater distance. These sensor satellites weigh about 250 grams each, using traditional materials like rigid PCB boards. Each one carries a sensor that always faces the asteroid, regardless of its orbital path. This ensures that the sensors can continuously gather data about the asteroid's surface composition as they orbit. The sensors themselves are a marvel of engineering. They must be able to withstand the harsh conditions of space, including extreme temperatures, radiation, and micrometeoroid impacts. Each sensor satellite is equipped with solar panels to provide the necessary power, and they use a technique called controlled reflectivity to adjust their orientation by reflecting sunlight. This method is not only efficient but also conserves energy, which is crucial for long-term missions in space. This engineering marvel is quite tricky. The sensor satellites must also point their solar arrays at the sun to get the 15 watts needed to operate the sensors and communication arrays. They use a technique called controlled reflectivity to adjust their orientation by reflecting sunlight. The coordination of these small sats is a significant challenge. Each satellite needs to communicate with the central hub and with each other to ensure they cover the entire asteroid surface without overlapping their observational fields unnecessarily. One of the major challenges in space missions is the handling and transmission of data. The sensor satellites collect vast amounts of data, which must be processed and transmitted back to Earth. This requires a robust communication system that can handle the high data rates and ensure that no information is lost. The Central Hub spacecraft plays a crucial role here, acting as a relay station that gathers data from the sensor satellites, processes it, and sends it back to Earth for further analysis. Once the data reaches Earth, it undergoes detailed analysis using advanced techniques such as time-of-flight mass spectrometry. This technique allows scientists to determine the composition of the debris plume created by meteoroid impacts. By analyzing the time it takes for particles to travel from the point of impact to the sensor, researchers can identify different elements and compounds present in the plume. This information provides insights into the asteroid's surface composition and structure. While this all sounds relatively straightforward in theory, there are many practical challenges to overcome, like controlling all the different satellites orbiting a single asteroid. This includes designing an overall architecture to manage these subsystems. The success of such a mission depends on precise engineering, extensive testing, and the ability to adapt to unexpected challenges. The implications of successfully mapping an asteroid's surface composition are immense. This information can help us understand the history and evolution of our solar system, identify potential resources for future space missions, and assess the risk posed by potentially hazardous asteroids. Moreover, the technologies developed for this mission could have broader applications in other areas of space exploration, such as planetary science and even interstellar missions. Currently, the development of MyDia is on hold, as it hasn't received a Phase 2 grant from NIAC or funding from any other source. But maybe someday, the thousands of asteroids in our vicinity will be mapped by swarms of tiny orbiters. The delay in funding highlights a common challenge in space research: securing the necessary resources to advance innovative projects. However, the interest and support from the scientific community and potential stakeholders remains strong. In conclusion, the Medea project represents a fascinating and innovative approach to asteroid exploration. By utilizing a swarm of small satellites equipped with plasma sensors, scientists can gather detailed data about an asteroid's surface composition. Despite the current funding challenges, the potential benefits of this technology are immense, promising new insights into the formation and evolution of our solar system and enhancing our planetary defense capabilities. So, what do you think about this innovative approach to asteroid exploration? Do you believe we'll see swarms of small satellites mapping asteroids in the near future? Let us know your thoughts and questions in the comments below. Thanks for watching, and don't forget to like, subscribe, and hit the bell icon for more exciting updates on space exploration and science. See you next time.